E-Physics class presented by Fatima Convent High School, myself Dipali. Light Reflection and Refraction, Chapter 10, Class 10. Let us see how the image is formed by a concave and a convex lens. We already studied the image formation by a concave and a convex mirror. There are quite similar concepts between the two, but let us see what have we to understand for the image formed by a concave and a convex mirror and a lens. Image formation by a lens. Lens forms image by refraction of light. We had studied that a mirror forms image by the formation of reflection of light, or you can say an image in a mirror is formed by reflection of light, whereas in a lens it is formed by refraction of light. This is the difference between the two phenomena. How do a lens forms image? What is their nature? Let us study this for a convex lens. Now always remember the characteristics of the image as we studied in the lens and in mirror is almost same. That is, you have to see whether the image is real or virtual, whether it is inverted or erect, size of the image and position of the image. These are the three characteristics we are going to take into consideration for the lens as well. Now, one more important thing you have to remember is the image formed by a concave mirror and a convex lens are similar, and image formed by a convex mirror and a concave lens are similar. So you can say these are in pairs. Now let us first see how it is done with the help of a activity, that is practically how the image is formed. Take a convex lens, find its approximate focal length in a way described in activity 10.11. Draw 5 parallel straight lines using a chalk on a long table such that the distance between the successive line is equal to the focal length of the lens. Place the lens on a lens stand. Place it on a central line such that the optical center of the lines lie just over the line. The two lines on either sides of the lens corresponds to f and 2f of the lens respectively. Now here f and 2f. F is the focus and 2f is the center of curvature. Which is also represented as C1 and F1 and F2 and C2. But we will use 2F and F. Now mark them with appropriate letters such as 2F1, F1, F2 and 2F2 respectively. Place a burning candle far beyond 2F1 to the left. Obtain a clear sharp image on the screen on the opposite side of the lens. Note down the nature, position and relative size of the image. Repeat the activity by placing the objects such as behind 2f1, between f1 and 2f1, at cf1, between f and o. Is it the same positions as we took for the concave mirror? Yes, because beyond, that is behind 2f1 at infinite distance, at beyond 2f1 is beyond c, between f1 and f2 is between f and c, and at f is at the focus, and between f and o is between pole and the focus, or here we will take as optical center. The nature, position and relative size of the image formed by the convex lens for various positions of the object is summarized below. Now you can see that here at infinity, the image position is at focus f2, highly diminished, point size and real and inverted. Beyond 2f1, between f2 and 2f2, diminished, real and inverted. At 2f1, at 2f2, same size, real and inverted. Between f1 and 2f1, beyond 2f2, enlarged and real and inverted. At focus f1, at infinite, infinitely large or highly enlarged, real and inverted. Between focus f1 and optical center O, on the same side of the lens as the object, that is enlarged, virtual and erect. So did you see the similarity between the image formed by the lens and the mirror? Now let us now do an activity to study the nature, position and relative size of the image formed by a concave lens. Take a concave lens, place it at the lens stand. Place a burning candle on one side of the lens. Look through the lens from the other side and observe the image. Try to get the image on the screen if possible. If not, observe the image directly through the lens. Note down the nature, relative size and approximate position of the image. Move the candle away from the lens. Note the change in the size of the image. What happens to the size of the image when the candle is placed too far away from the lens? The summary of the above activity is given in table 10.5 below. So, is it same now as we did for a convex mirror? At infinite, at focus f1, highly diminished, point size and virtual and erect, and between infinity and optical center O of the lens, that is between focus f1 and optical center O, diminished, virtual and erect. What conclusion can you draw from this activity? A concave lens is always given a virtual, erect and diminished image irrespective of the position of the object. Is this clear? Now let us see how we can use it by studying a ray diagram. We can represent image formed by a lens using a ray diagram. Ray diagram will also help us to study the nature, position and relative size of the image formed by the lens. For drawing the ray diagram in lenses, unlike a spherical mirror, we consider only two of the following rays. A ray of light from the object parallel to the principal axis after refraction forms a convex lens, passes through the focus on the other side of the lens. In case of concave lens, the ray appears to diverge from the principal focus located on the same side of the lens as shown in the figure. So you can observe the difference between the image formed, the ray diagram for the concave mirror and concave lens, convex mirror, convex lens and convex lenses. Now, second, when we take a ray of light passing through the principal focus after refraction forms a convex lens while emerge parallel to the principal axis. This is shown in the figure 10.12. A ray of light appearing to meet at the principal focus of the concave lens after refraction will emerge parallel to the principal axis. This is shown in figure 10.14. So, you can observe that after refraction how it forms. The ray of light passing through the optical center of the lens will emerge without any deviation. This is illustrated in figure 10.15 and figure 10.15b. The ray diagram for the image formed in a convex lens for a few positions of the object are shown. The ray diagram represents the image formation in a concave lens for various position in the object is shown below. Now you can observe here very clearly that if the object is kept at an infinite distance, then the incident ray and the principal axis are parallel to each other. The ray starts diverging or changing its direction at the aperture, and so we know that it is a converging lens. So after refraction they will meet at one point, that is focus f2. I hope this is clear to you. So you can clearly observe this image formed by the position at infinite distance is at the focus. It is real, inverted, point size. Now let us see the second position for the object placed beyond 2f1. That is, when you take the incident ray and one ray passing through the optical center, you will see that they meet at a position between f2 and 2f1 on the other side of the lens. So it is real, inverted, between f2 and 2f2, and it is smaller than the object. Same thing when you go for the third position. Now you have at f1, at 2f1, that is at C, then you find the image formed same again at 2f2 on the other side, which is real and inverted, same size. And between 2f1 and f1 we get it beyond 2f2, that is larger than the object, and it is real and inverted. So now let us check position at f1. When it is f1, then you get the image formed at an infinite distance, and if it is placed between f1 and O, it is formed on the same side, that is a virtual image is formed between at infinite distance, which is seen in the diagram. Now when you have a concave lens, then the same as infinite, it is formed at f, and if it is anywhere between infinite to O, it is always formed beyond f1 and between f1 and 0, that is O. That is the position of the image formed by the concave and convex lenses and the characteristics of the image. That table is very important to be learnt. Now let us see the sign conventions for spherical lenses. For lenses we follow sign conventions similar to the ones used for spherical mirror. We apply the rules of signs of distance, except that all the measurements are taken from the optical center of the lens. According to the convention, the focal length of the convex lens is positive and that the concave lens is negative. So that is very clear from this topic. You must take care to apply appropriate signs for the value of u, v, f, object height h and image height h prime, that we have already studied in the concave and convex mirrors. Now lens formula and magnification. As we have a formula for spherical mirrors, we also have the formula for spherical lenses, and this gives the relation between object distance, image distance and focal length f. The lens's formula is as expressed below. 1 upon v minus 1 upon u, 1 upon v minus 1 upon u is equal to 1 upon f. The lens formula given above in general is, and it's valid in all situations for any spherical lenses. Take proper care for the signs of the different quantities while putting numerical values for solving problems related to lenses. So did you understand what is the mirror formula and what is the lens formula? And what are the different sign conventions? Let us understand the topic magnification now. We already understood what is magnification, the ratio of image height upon object height. The magnification of the product produced by a lens similar to that of spherical mirror is defined as the ratio of height of the image and the image of the object. Magnification is represented by letter m if m is the height of the object and h prime is the height of the image given by a lens. Then magnification produced by the lens is given below. M is equal to height of the image upon height of the object is equal to h prime upon h. Magnification produced by a lens is always related to the object distance u and the image distance v. This relation is given by magnification m is equal to h prime upon h is equal to v by u. The difference is in mirror it was negative, here it is positive. Now let us solve a numerical based on this formula. A concave lens has focal length of 15 cm. At what distance should an object from the lens be placed so that it forms an image at 10 cm from the lens? Also find the magnification produced by the lens. The concave lens always forms a virtual erect image on the same side of the object. Image distance v is minus 10, focal length f is minus 15, object distance u you have to find. So since 1 upon v minus 1 upon u is equal to 1 upon f, or 1 upon u is equal to 1 upon v minus 1 upon f, replacing the values from the question, we get u is equal to minus 30 centimeter. Thus the object distance is 30 centimeter. Magnification m is v upon u. So m is equal to minus 10 upon minus 30 is equal to 1 upon 3, that is equivalent to plus 0.33. The positive sign shows that the image is erect and virtual. Image is 1/3 of the size of the object, means it is smaller than the size of the object. Let us see one more example. A 2 cm tall object is placed perpendicular to the principal axis of the convex lens of focal length 10 cm. The distance of the object from the lens is 15 cm. Find the nature, position and size of the image. Also find its magnification. So, what is the solution? Height of the object h is plus 2 cm. Focal length f is plus 10. Object distance u is minus 15. Image distance v we have to find. Height of the image h prime we have to find. Applying the lens formula, 1 upon v minus 1 upon u is equal to 1 upon f, or 1 upon v is equal to 1 upon u plus 1 upon f. We replace the values from the question, we get v is equal to plus 30. The positive sign of v shows that the image is formed at a distance of 30 cm on the other side of the optical center. The image is real and inverted. Magnification m is h prime upon h is equal to v upon u, or h prime is equal to h upon u upon v upon u. The height of the image h prime is minus 4 cm. Magnification m is v upon u, that is minus 2. The negative sign of m and h prime shows that the image is inverted and real. It is formed below the principal axis. Thus, a real inverted image 4 cm tall is formed at a distance of 30 cm on the other side of the lens. The image is 2 times enlarged. So, did you understand how we are applying the mirror formula to get an idea about the characteristic, position and size of the image? I hope this concept is very clear to you now.